Out there in the vast expanse of the cosmos, dramatic events occur that dwarf anything we experience on Earth. Imagine an explosion so powerful that it briefly outshines an entire galaxy. This is the awe-inspiring power of a gamma-ray burst, or GRB. These bursts release an unimaginable amount of energy in the form of gamma rays, the most energetic form of light in the electromagnetic spectrum. GRBs are not just fleeting bursts of energy, they are reminders of the dynamic and often violent nature of our universe. The discovery of GRBs was accidental, a serendipitous finding during the Cold War. In the 1960s, the United States launched the Vela satellites to monitor nuclear weapons testing. These satellites picked up bursts of gamma rays coming from space, not from Earth. This surprising discovery sparked a wave of scientific curiosity. What were these powerful bursts, and where were they coming from? Initially, there was speculation that GRBs might originate from within our own galaxy, the Milky Way. However, as astronomers studied more GRBs, they realized that these bursts were coming from incredibly distant galaxies, billions of light-years away. This realization only deepened the mystery. What could be powerful enough to generate such intense bursts of energy across such vast cosmic distances? Astronomers have narrowed down the origins of GRBs to two main scenarios, both involving the death throes of massive stars. The first and most common scenario is the collapse of a hypernova. Hypernovae are essentially superpowered supernovae, the explosive deaths of stars much more massive than our Sun. When these giant stars exhaust their nuclear fuel, they can no longer support themselves against the relentless inward pull of gravity. The core collapses, forming a black hole, and jets of particles are blasted outward at nearly the speed of light. These jets pierce through the collapsing star, releasing gamma rays as they erupt into space. The second scenario involves the collision of two neutron stars. Neutron stars are the incredibly dense remnants left behind after a supernova explosion. They are so dense that a teaspoonful of neutron star material would weigh billions of tons. When two neutron stars spiral inward and collide, the result is a cataclysmic merger that also produces jets of particles and a burst of gamma rays. These neutron star mergers are now also recognized as sources of gravitational waves, ripples in the fabric of spacetime. The sheer power of GRBs is awe-inspiring, but it also raises a sobering question: could a GRB ever pose a threat to life on Earth? The answer, like many things in astronomy, is complex and involves probabilities. GRBs are detected almost daily by orbiting telescopes, but the vast majority of these events occur in galaxies billions of light-years away. The probability of a GRB occurring close enough to Earth to pose a direct threat is extremely low. However, just because the probability is low doesn't mean it's impossible. Astronomers estimate that a GRB could occur within 3,000 light-years of Earth, close enough to affect us, roughly once every few hundred million years. While that may seem like a long time, it's important to remember that Earth is about 4.5 billion years old, and life has existed on our planet for billions of years. Over such vast timescales, even relatively rare events become more likely. Section 4. The ozone layer, our fragile shield. To understand the potential consequences of a nearby GRB, we need to look at how these bursts interact with Earth's atmosphere. One of the most significant effects would be the destruction of the ozone layer. The ozone layer, located in Earth's stratosphere, plays a crucial role in protecting life on our planet by absorbing most of the sun's harmful ultraviolet radiation. Without the ozone layer, life on Earth's surface would be exposed to lethal levels of UV radiation. The intense gamma rays from a nearby GRB would ionize molecules in Earth's atmosphere, triggering a cascade of chemical reactions. These reactions would lead to the destruction of ozone molecules, thinning, or even temporarily eliminating the ozone layer. The duration and severity of ozone depletion would depend on the distance and intensity of the GRB. Section 5. A toxic cocktail: photochemical smog. Beyond ozone depletion, a nearby GRB could also trigger the formation of photochemical smog on a global scale. Photochemical smog, also known as Los Angeles smog, forms when sunlight interacts with nitrogen oxides and volatile organic compounds in the atmosphere. These pollutants come from vehicle exhaust, industrial emissions, and other sources. The intense radiation from a GRB could break down atmospheric nitrogen and oxygen molecules, creating nitrogen oxides. These nitrogen oxides, combined with existing pollutants in the atmosphere, would react with sunlight to form a thick brownish haze of photochemical smog. This smog would not only reduce visibility but also pose serious health risks to humans and animals. Section 6. Echoes of Extinction, GRBs and Earth's Past. The potential consequences of a nearby GRB, from ozone depletion to the formation of toxic smog, raise a haunting question. Could these cosmic events have played a role in shaping the history of life on Earth? Some scientists believe that GRBs may have been responsible for past mass extinction events, wiping out vast numbers of species and resetting the evolutionary clock. One of the most compelling pieces of evidence linking GRBs to mass extinctions comes from the Ordovician-Silurian extinction event, which occurred about 440 million years ago. This event, the second largest extinction in Earth's history, wiped out an estimated 85% of marine species. Some scientists have proposed that a GRB, occurring relatively close to Earth, could have triggered this extinction event by damaging the ozone layer, disrupting the food chain, and altering the climate. Section 7. Unraveling the Mysteries Studying GRBs. While the possibility of a GRB directly impacting Earth is remote, studying these events provides valuable insights into the extreme processes occurring in the universe. Astronomers continue to study GRBs using a variety of telescopes and observatories, both on the ground and in space. These observations are helping us understand how GRBs form, what types of stars produce them, and how they affect their surroundings. One of the key tools for studying GRBs is the Swift Gamma-Ray Burst mission, a NASA satellite launched in 2004. Swift acts like a cosmic detective, rapidly detecting GRBs and then quickly pointing its telescopes to study the afterglow. These afterglows, which can linger for hours or even days after the initial burst, provide valuable information about the GRB and its environment. By studying GRBs, astronomers are not only unraveling the mysteries of these powerful cosmic explosions, but also gaining a deeper understanding of the universe we live in. These studies also serve as a reminder of the importance of protecting our planet and its fragile biosphere from both terrestrial and cosmic threats. Don't forget to like, share, and subscribe for more cosmic content.